And also infamous because he was responsible for the ritual humiliation of many, many string theorists all at once, when Jeff Harvey, aided and abetted by Clifford Johnson, made us all do the Maldacena at a banquet. Well, Juan has now consented to present a new dance to us, and he's going to be talking about PP waves.
Strings on PP waves. Okay, it's a pleasure to be here. Can you hear me? Is the microphone on? Yeah? Okay. The talk will be basically divided into two talks. The first half will be based on this paper that we wrote with Bernstein and Nastase, and well, some other subsequent papers. And the second part will have to do with some worldsheet dynamics on PP waves, or some interesting PP wave spacetimes. And that is based on some work I did with my student Liat Maoz, and also with Nathan Berkowitz. So we know that type 2B strings on ADS 5 cross S5 is the same as n equal to 4 Young mills on S3, and where the radius of the ADS or S5 space is given by, in terms of the Toft coupling, through this formula. N is the number, the flags of the Ramon 5 form, and it's the number of colors of the Young-Mills theory. Now, when we have this relationship, we have here ADS times a sphere, so this is the space-time, the gravity version, and here we can have some states which have some energy measured with respect to global time, and those states should be in one-to-one correspondence to states of the Young-Mills theory on S3, where the Young-Mills theory is defined on S3, so on the boundary of this, of ADS5 times time, so we have the usual time evolution on the boundary, and any state with some energy E here corresponds to a corresponding state on the Young-Mills theory with the same energy E. Now, when we have a conformal field theory, it's sometimes convenient to describe these states in terms of operators inserted at the origin of the Euclidean theory on R4. So there is this correspondence between states of the Lorentzian theory or Euclidean theory on S3 cross R and the operators inserted at the origin in R4. And according to this relationship, the state with energy E will correspond to an operator with conformal dimension delta. So delta is equal to E to the energy of the state. Now we can take the so-called plane wave limit of this, and what we do is the following. We consider a state in ADS which is sitting at the center of ADS, so this is a spatial cross-section of ADS, and it's moving rapidly on S5, and with some large angular momentum. J is the angular momentum in one of the directions of S5. So this angular momentum J is the same as U1 charge of the corresponding operator, and under SO6, which is the R symmetric group of the theory. It's a global symmetric group of the theory. So we take the limit when J goes to infinity and R goes to infinity, so the radius of ADS gets very large, and keeping this combination fixed. So in terms of the gauge theory variables, this is the R charge of the operator and the square root of the Toft coupling. That's being kept fixed. And if you take this limit, then the geometry of ADS 5 cross S5 goes over to a plane wave geometry, where plane wave geometry is this geometry here, which is essentially R10 plus this factor, and this is the only factor by which it differs from R10. So it's a very simple metric, and the momentum P lower minus, so this is the momentum that generates translations in X minus, is given by J over R squared, so a quantity that remains fixed, so in this limit. And P lower plus is the one that generates translations in X plus. That's given by the difference in between the conformal dimension of the operator and its J charge. It's U1 charge. Now, one nice thing about strings on plane waves is that whenever we have a covariantly constant null Killing vector, as in this case, so that's the Killing vector equal to d dx minus, then one finds that the string, the worldsheet string action, simplifies in Lightcone gauge. So we choose x plus equal to tau, and then use the equation of motion for x minus and so on to fix the momentum, p lower minus. And so we find the Lightcone gauge action, which is very simple in this case of a plane wave. So we have just the terms in blue are the terms we would also get in flat Minkowski space. And the only difference is these extra green terms. So one is a mass term for the transfer scalars, and that comes from the G++ component of the metric. The fact that since x plus is equal to tau, so d of x plus just a constant, and that's why we get this term here. And similarly, we get a mass term for the fermion fields that comes from the coupling of these Green-Schwarz fermions to the Ramon-Ramon fields. So we can easily quantize this action by expanding all fields in Fourier modes. And when we do that, we find that the Lightcone Hamiltonian, which generates translations in x plus, so that therefore is equal to p lower plus, is the same as, the energy in this set of harmonic oscillators. So for each Fourier mode, we have a harmonic oscillator whose frequency is the mass plus the term coming from the momentum, and it has this form. And so we can express these quantities in terms of the gauge theory variables, and we find that delta minus j, so the conformal dimension of the operator, is given as this sum, where each term looks like square root of 1 plus the Toft coupling times the mode number of the oscillator, the Fourier mode of the oscillator, n divided by j squared. So we see in this expression that if mu is very small, we recover the flat space, the flat space equations. Now we can form the corresponding Yang-Mills operators, and we do that by constructing the operator C, which is a combination of these two transfer scalars, which is charged under this U1 symmetry. So this U1 symmetry, we take it to be the one that rotates the 1-2 plane. And so we have this operator trace of C to the j. That operator has delta equal to j and corresponds to the Lightcone, to the vacuum in Lightcone. This operator is BPS, so we know that even if we include quantum corrections, it will still have delta minus j equal to 0. Now, we can similarly construct operators which result from the creation of zero modes, so of zero momentum modes. So if you have an oscillator corresponding to a field which on the string worldsheet has no momentum, you can act that oscillator in the Lightcone vacuum, and one can find the corresponding string state, the corresponding operator, because the action of these generators, the action of these massive modes, comes from the action of some space-time symmetries which are not preserved by this state. So when we act with them, we generate a new state, which is this one. And similarly, we can act with the same symmetries on the left-hand side and find that this is the corresponding operator. So if this oscillator has some index in what were originally S5 directions, so directions in SO6 which are not the 1 and 2 directions, but let's say 3 and 4 and so on, then we get that one of the C's gets exchanged into one of the other phi's. So W is either phi 3, phi 4, phi 5, or phi 6, and so we get this operator. Now we can. Now the idea is that if we act with an oscillator which on the string worldsheet has non-zero momentum, that corresponds to the same thing as what we had before, except that now we don't average over all the positions where W can be inserted, but we sum over all positions with some phase which is proportional to n. Now, if we are acting with many oscillators, we will insert different W's or psi's or other fields in different positions. We add with some phases, and we'll get, that's the answer for what the corresponding operator is. Now, when we make this correspondence, we find that the fact that the trace is cyclic implies that these operators constructed in this fashion will automatically vanish, unless the total momentum, unless the sum of all ni's, which can be interpreted as the total momentum on the string worldsheet, is equal to 0. And indeed, those states are not really in the string spectrum. So they are states of the 2D conformal of the 2D field theory, but they are not states in the translations. So one can so for very small Toft coupling, one finds that the conformal dimension of these operators, each time we insert a W, some other field here, delta minus A will increase by 1. So that's just the conformal dimension of this field W. And if we are in the free theory and we consider just planar diagrams, when we insert the W in some position, when we compute the 2-point function of O with O bar in order to compute its conformal dimension, we'll find that W cannot change positions. Okay? However, once we include interactions, this W can start exchanging positions. And when we do that, we will find that the conformal dimensions will start depending on the value of the momentum. And so this is the result we find at one loop. And the coefficient is such that it agrees with the strong coupling result that I presented in the previous transparency. So this is a calculation that we do for G square when G square n is very small, while the other calculation is a calculation we do with when G square n, G square big N is very large. Now there was an argument by Sant'Ambrosio and Sanon, which argues that indeed this conformal dimension is given by this full square root formula to all orders in the in Gn. So they managed to present an argument that by which one can compute exactly this formula, and so they derive from the field theory the formula that one had from the string theory. And so using this result, one can even go to values where J is very small and have the flat space limit. So in this formula explains why you get strings from Yang-Mills theory in the flat space limit. So one of the surprising aspects of ADS-CFT is that for large values of the Toft coupling, we have strings in almost flat space, and this is explained in that point. So what we find in these operators is that this string of C's, so one C after the other, define a lattice, and other excitations move along this lattice. Taking the J equal to infinity limit is like taking the continuum limit. So in that sense, these C's are like string bits, and we find a precise match in the string spectrum. Okay, that was the end of the first part of my talk. Now I'll go on to the second part of my talk. So the idea in the second part will be to study backgrounds with Ramon-Ramon fields, which have this plane wave form, this PP wave form. So we'll have essentially R10 plus this factor. And now this function G++ will not just be quadratic function, but will be a more complicated function of the transverse coordinates. And then we'll consider non-constant phi form. So this 4 form here will also be not constant. And the aim is, the objective of this exercise is to find some interesting interacting theories in the Lightcone. So we'll see that we'll find some theories that are solvable, are interesting, and have interesting duality properties. And there are not many examples of strings that we can solve with Ramon-Ramon fields. The only known example is this one with of the plane wave form. So it would be nice. It's nice to study more solvable examples of strings with Ramon-Ramon fields. So we'll restrict, for reasons you'll see in a second, to theories with well, we'll consider in particular theories which have 2, 2 supersymmetry on the worldsheet once we are in Lightcone gauge. So the Lightcone gauge action will be a 2, 2 supersymmetric theory. So we look for backgrounds which such that when we write the action in Lightcone gauge, we have the usual, so this is just the flat space part, plus an arbitrary superpotential. Okay? And you can check that given any arbitrary superpotential, you can find the gravity background such that when you reduce strings in Lightcone gauge in that background, you get this 2,2 superconform. This 2,2 theory, field theory, is not conformal because of this term. This 2,2 theory with an arbitrary superpotential. And so you can write down what this 4 form is in terms of the superpotential. And basically the expression looks like, well, the derivatives of the superpotential times some 3-1 forms. There are 10 3-1 forms, the same number as there are derivatives of the superpotential. I mean, we have 4 fields, the 4 complex transverse dimensions. And well, more explicitly, it's this expression. And similarly, the G++ factor in the metric is equal to the derivative of W. I mean, you can clearly see that these derivatives of W should appear in the 4 form since they are, so the 4 form will act as a mass term for the fermions. And indeed, when you have this action in superspace, once you integrate out the theta coordinates, you find that the mass terms for the fermions are proportional to these derivatives of W. Now, if you have a generic superpotential, and so, well, this function is rather generic, then there are only 4 space-time supersymmetries. So the 4 space-time supersymmetries will be the ones that then become these 2,2 supersymmetries in Lightcone gauge. And these are supersymmetries which anti-commute to P+, so they anti-commute to the Lightcone Hamiltonian. Now, some of you who have read some of the PP wave, the plane wave literature, might have noticed that there are always 16 supersymmetries that anti-commute to P-. And that's the case only when the plane wave is quadratic. That's not the case anymore when you have a generic W. And the basic reason for this is that each of these supersymmetries that anti-commutes to P- essentially means that you have a free fermion on the worldsheet. Because these anti-commutation relations, once you fix P-, are the anti-commutation relations of essentially a free fermion. That's only the 0 mode of the free fermion, but then by Lorentz invariance on the worldsheet, you have the free fermion. And since for a generic W, none of the fermions is free, you will have none of those supersymmetries. Now, one question one can ask is whether these are really string solutions. So I've shown you that, well, one can check that they are solutions in supergravity, that they are actually they are supersymmetric solutions in supergravity, but that would be the sort of at one loop in alpha prime. So how does one check that they are full string solutions? Well, one has to use one has to use the Berkovits formalism to be able to even write down those equations in a meaningful way. And a formalism of his that is very useful is is a formalism which preserves SU4 cross U1 symmetries. And it's such that this is a formalism in which one can think of the string, one can think of the n equal to 1 string as an n equal to 2 critical string. And so checking the equations of motion boils down to checking that the model is 2,2 superconformal invariant, and it seems that one can check that, though this is work still in progress. So we believe we have checked that, but we're not too sure yet. Now, let me say some generalities about the solutions. So, in these solutions, we have a non-trivial RG flow on the worldsheet. So since the theory is massive, the theory at high energies and low energies looks very different. And the RG flow on the worldsheet corresponds to boosts in the x plus and x minus directions. So in space-time, small p lower minus corresponds to space-time that is almost flat. It corresponds to small Ramon-Ramon fields. And that corresponds in the worldsheet side to the UV of that massive field theory. It corresponds to a free field theory. So since this is a massive field theory, the theory plus the superpotential in the UV, the superpotential is not important, and we have the usual free conformal field theory of flat space. On the other hand, we can consider large p lower minus, and that corresponds to high curvatures or high tidal forces. I mean, the curvature scalar is 0 for these backgrounds, but there are large tidal forces. And that corresponds to the infrared of this massive field theory. And so since this is a field theory that is massive, we will generically have a mass gap. And so in the infrared, we'll have a very long worldsheet. I mean, say very long because the size of the worldsheet. So the reason that small p minus is the UV and large p minus is the infrared is just that p minus sets the length of the worldsheet. So for small p minus, we have a very small one, and for large p minus, a very large one. And in this side, we'll have some massive particles that are moving along this string. And well, there can be different numbers of massive particles. So the number of massive particles is not necessarily equal to 8, the number of transverse dimensions, but we can have any number, as you will soon see. Okay. Now, one thing you can do with this is that you can consider integrable models. So there is a lot of literature on integrable models. And as a particular example, we could consider the n equal to 2 sine Gordon theory, but there are others. So that's a theory with this Lagrangian in superspace. And just to give you some orientation, once you write this Lagrangian in superspace, you integrate out the theta coordinates, you find that the bosonic, for example, the bosonic potential for this model is a cosh rho and a ordinary cosine of phi. Now what we'll do later, we'll choose to compactify this phi coordinate. Now of course we can choose whether to compactify or not. We'll now consider the model where we compactify it. The particle spectrum of this model, so these particles are the particles that move on the worldsheet when the worldsheet is very long, has this form, and this is a result that one can derive exactly because this model is integrable. And so the number of particles depends on beta. So for very large, so depending on what beta is, we'll have different numbers of particles at low energies. So at long distances. So this ms is the mass of the solitons, of the sine Gordon solitons. So the solitons that interpolate between two vacua of this cosine, and so on. Now, unfortunately, even though the model is integrable, it's hard to find the exact spectrum for any given length of the worldsheet. So when you put an integrable theory in a compact circle, it's hard to find the spectrum. However, it is possible to find the spectrum for large L, where you can use the Bethe ansatz and the precise S matrix. And there will be some questions that you can answer in terms of the exact S matrix. So small beta corresponds to the semi-classical limit of the sine Gordon model. And so for small beta, this circle is very large. So the target space is essentially a cylinder because we have compactified the phi circle times an infinite rho direction. So we saw the bosonic potential was, or G++, the redshift factor in the metric, is proportional to this cosine hyperbolic. So a string will be localized in this region, will be pushed to this region. And then we have cosine of 2 beta phi. So there are two minima of these cosines, or at least the two vacua of the sine Gordon theory. Now, so this is fine. Now, an interesting limit to take is to consider the large beta limit. And so this corresponds to strongly quantum sine Gordon theory. If we remember the previous formula for the particle spectrum, so what was the fundamental particle of the sine Gordon model disappears there. We are only, well, what one might have thought is the fundamental field of the sine Gordon. The particle associated to the fundamental field disappears. We are only left with the soliton and anti-soliton. And so we can ask, well, what does that correspond to? And here we see that the large beta limit corresponds to taking this circle to be very, very small. And we can do a T-duality in that circle. Now, that T-duality is really a mirror symmetry transformation, as well of the type Hori and Baffa discussed. And this, when you do that mirror symmetry transformation, what you get is the so-called sausage model. So now the radius of this circle is going to be proportional to beta. So if beta was very small, this dual radius is very large. And so we have a sausage. So essentially we have a sigma model on this sausage. In the case beta equal to infinity, that was discussed by Fendley and Intriligator, and then it was also discussed by Horry and Kapustin. Now this is the form sphere, and we know that sigma models on non-Ricci flat manifold are not conformal, and indeed this theory is not conformal since it's related to a massive theory, and the mass scale of this theory is related to the size of this sausage. So the size is proportional to the energy we are considering in the theory divided by that mass scale, where the mass scale is the mass scale of the sign related to the mass scale of the Sine-Gordon theory. So this is the well-known, the duality between the pendulum and the sausage and the hot dog. Now, one interesting limit to analyze is the limit of beta equal to infinity, not just very large, but equal to infinity. And in that case, we get around CP1, 2, and the theory becomes SU2 invariant. And so for small, and this is a very surprising background because for small p minus, we see so strings which have very small p minus see a very large CP1, and strings with very large p1, very large p lower minus see a very big, very small space. So this is sort of the opposite of what Lenny usually likes to say, that objects grow when they are boosted. This is roughly the opposite. The space shrinks when you look at it from a boosted frame. Now, one interesting question for which I don't have a good answer is what the string background, so the covariant background, that gives rise to the CP1 model in Lightcone gauge. Now, so there is a conformal field theory, and one can actually write that conformal field theory in the original Sine-Gordon variables using the Berkovich sigma model, but one would like to do it already in these two dual variables. And usually the way you get massive theories, as the way we got the massive theory in the first place, was that the mass scale of the Lightcone gauge theory comes from the fact that dx plus has some expectation value, and so terms that have the mass appear in this simple form come from these terms in the metric, but in our case we have the mass scale appearing in this funny way, so it looks like in this background there are higher massive stringy modes that are excited. So finally, let me conclude by saying that we find the class of backgrounds which are the PP waveform that lead to interacting theories, and this mirror transformation leads to surprising backgrounds. They are surprising because they are very, very big. They can be very, very big, and in order to stabilize them, in order to understand why they solve the equations of motion, we need to invoke these very massive string modes. These backgrounds are not obvious solutions of supergravity in any way that I can see, these T-dual backgrounds. Thank you very much.
Time for a couple of questions.
Yeah, Gary.
Gary Gibbons, Cambridge. Interesting if you replace the flat directions by some spin 7 manifold or something of that sort?
Yeah, so you can do this. I didn't describe this here, but you can replace this 8-dimensional manifold by an 8-dimensional Calabi-Yau space, for example. And then the statement is that you can still add an arbitrary superpotential. Okay.
Only for Calabi-Yau or spin 7?
Well, you could, in principle, do spin 7, I think, but we haven't analyzed that possibility. That would probably have only 1-1 supersymmetry.
Any other questions? Well, sure.
Yeah, Shiraz.
Suppose you were given suppose you were given a theory on the world sheet and told that it was the theory that you got in Lightcone gauge from fixing to Lightcone gauge from a conformal field theory. Are there general constraints that apply to the Lightcone gauge theory that necessary or sufficient or?
I don't know what the constraints are. So for this n equal to 2 theories, it looks like an arbitrary n equal to 2 theory, at least with an arbitrary superpotential solves the constraints. However, for example, if you start putting transverse scalar space, looks like it has to be flat, at least at one loop, right? So at least at the level of supergravity, you see that there are some constraints. But I don't know how to state the most general constraint. And when I started this, I would have thought that something like the CP1 model was not possible, but it seems to be possible due to this chain of reasoning. So.
I think we both